variety of awards, and he's doing outstanding things in the area of trying to broadcast science to the masses, and you can see the QR code for the Holy Shift podcast up here, which he is a producer of at Georgia Tech Emory, so I certainly encourage you to check that out. So he's an outstanding lecturer, and we are and a good friend, and we're super fortunate to have him here with us today.
Thank you for the kind introduction. So today I thought we would talk about something called hybrid models. And the idea is that we can learn about the physiology that we're interested in using model systems, but some of these systems have limitations. So what's an example of a model system? It might be like a set of equations or something that represents activity that you're interested in, features of the system you're interested in. That's a model of a system. Or it might be a mouse, right? So we do genetic testing or drug testing on a mouse. We don't usually really care what happens in the mouse. What we usually care about is how that represents what happens in a person, right? So the mouse then would be a model system of a person. So I want to talk about how we can combine different types of models, put the pieces together to extend each one of their capability. And I want to talk to you about that in two systems, both of which Josh mentioned already. The first is in brain-device interfaces, and the second is in restoration of lost bladder function. So they're kind of two stories, but the theme is the same in both. It's how can we push the boundaries using new types of models. We'll start by talking about brain-computer interfaces. Okay, what is that? Has anybody heard of a brain-computer interface? Yeah. Okay, all right, that's more hands than I got, 6 years ago. But the idea is for the most intense versions of them, this is one of the earlier ones, you put an array of metal probes inside the tissue of the brain, usually in somebody who is almost fully paralyzed. And the goal is to record what the nerve cells are doing and guess in some rudimentary way what that person wants to do, and then we can make that happen for them. And in that way, they've got a lot more independence. They can do things they couldn't before because of their paralyzed body. Here's just some examples, right? You might want to control your power wheelchair, or a robotic arm, or play music, do computer games, or if you're the Department of Defense, maybe you want your fighter pilots to fly, their jets, right? Things like that. But here's the problem. Nobody wants to have electrodes implanted in their brain, right? That's a big ask. I don't know how many of you would be interested in having that done, but normally it's a method of last resort. It's only when you have no other options left available would you consent to using technology of this kind. So we don't have many people on which to test and develop the technology. After all, how are we doing this translation from neuron activities into a person's intent? Right, we got to figure that out, but unless we can test it in a bunch of people, we don't know how to do it. But until we know how to do it, people don't volunteer. So you can see we're kind of stuck in this cycle. And if anyone has taken basic design of science courses, you know that if you test something in one or two participants or experiments, you don't have a good idea about the true underlying nature of the thing you're testing. You need many samples. This is the bell curve, right? The Gaussian distribution that you see. So we can figure out what's really going on. We need more samples. Okay, so let's talk about models to solve this problem. Here's the baseline case. We've got a human participant. We are recording signals from their brain. This is the abstract chatter of their neurons. We decode that information, and this is the process of pulling out intent from the signals, and then we activate what they're doing with their computer cursor based on what we think they want to do. But this is the case where we only have one, maybe two participants, right? Even Elon Musk, I think still the world's richest person, give or take, has this whole company based on this. For years, been working on it. He has what? I think the current count is 5 participants, right? So even if you've got all the resources in the world, right, this is still a problem. One solution that people have come up with is say, well, let's just take all the data we've already recorded from all these people, and we'll put it on a hard drive somewhere. I don't even know if people know what this is, right? This is a floppy disk, what I used to put my data on when I was a kid. So now we've got all these neural activities. They're stored on the computer. We have an idea of what the person wanted to do, because let's say we ask them to try to do something. And then we build the translator based on this. Great. And then we to lay out the roadmap. And this is what we came up with, where every one of these lines is a model of the form that I showed you. That was my entire postdoc experience. And just so you get the idea, I'm labeling this one particular line as the urethra nerve model, right? And we would need one for every one of those things. And then we would need another model to navigate the interaction between all these other models, right? And just figuring out what we needed took 6 or 7 people. Okay? So this is, I mean, maybe this is going to happen, and maybe we'll have this computational model of the lower urinary tract someday, but certainly no time soon. And so the question is, in the meantime, while we are missing all of these pieces that are shown in the dashed lines, is there anything that we can do? And here is the proposed solution from the lab. You will not be surprised that it is a hybrid model, and that's what we're proposing. And this is a slide that I showed here, I think in 2001, about the overall concept of the project, and it's still the same. Okay, so the problem is, if we want a traditional mathematical model of the lower urinary tract, you need every single piece of the puzzle, otherwise nothing runs. So the idea is, let's just take the pieces that we know, right? Those ones that we've already got models for, we'll use, like the one I made of the urethral sensory neurons. But then everywhere where we don't have a puzzle piece, which represents a traditional mathematical equation, we'll stuff in AI somehow. And when we run this whole thing, the AI will kind of learn the missing puzzle pieces. They will approximate the puzzle pieces that should go there. And once we've got that in place, we have a hybrid traditional mathematical and modern AI mathematical model, and we can use that to test different treatment options, right? So if we want to know what happens if we stimulate this nerve, does that fix overactive bladder? Well, we can stimulate that nerve in this hybrid model. And even if we don't know all of the physics as written in traditional differential equations, the AI will take care of the missing pieces. That's the concept. All right, how in the world would you train such a thing? Because normally when you train AI models, everything from image recognition to large language models, what you do is you've got a giant pot of parameters and you keep throwing examples at it until the parameters give you back what you're requesting based on the input. But if it's all stuffed into these other differential equations, how can you give it those examples? So a big part of this project was figuring out how could we train hybrid models of this kind. So I'll walk you through it at a high level. Here you can imagine, like this is the puzzle I showed you, right, this purple patch. We've got some ordinary differential equations, and those are the puzzle pieces we know. We can write down the math. And then we've got some artificial neural networks in there. And the thing is, we take every one of these small artificial neural networks as a proxy for one puzzle piece. So we don't have some big model that all the data goes at. We've got a bunch of small models, neural networks, each one circumscribed to represent one of the missing puzzle pieces. And in that way, it makes understanding the input-output range of those models much easier to handle. And on top of that, we know what they're supposed to represent. Because one of the big problems with traditional AI models is you don't know what's going on inside. But here, we know at least the input-output of whatever this is supposed to be, because we've explicitly said it's supposed to represent this tissue or this neuron or something. Now, for anyone who is in or has taken BME 2740, what we do now is numerically integrate this system of differential equations. And you can see, right, this is the derivative of every one of the physiological states coming out. So that could be things like the pressure in the bladder and how much sensory activity is coming off of a neuron, or all these kinds of things. So we've got this whole list of physiological states, and this is their rate of change. And we multiply that by the time step, right, dt, and then we add it to what it was before, and this is like classic Euler's method of numerical integration to get the next moment in time. We experiment with this numerical integrator, right? We do some more sophisticated things, but this is the general idea. The problem is that, of course, these things are total nonsense at the beginning, right? Because we don't know what the approximations should be, so we're not getting good results. Okay, so how do we start training these things? Here's one of the tricks we do. We pull all these physiological states, again, things like bladder pressure, urethral pressure, flow rate, motor neuron discharge, right? These kinds of physiological states you might hear about. We pull them down here, and we append to them the parameters of these neural network models, these puzzle piece approximations. So now we've got what I'll call an expanded state. So not only is it the traditional physiological states we care about, but also it's the neural network weights. So we've got like a bunch of things like bladder pressure floating around, and also these very abstract parameters. What we use is a Kalman filter, or some variant of that, and that's like the thing that tracks where your car is when you're running Google Maps or whatever. It's a Kalman filter running to estimate your position. So it's like that, right? It's something that estimates states of things and how they change. So we put that expanded state into the filter, and we ask the filter to predict, okay, what do you think all of the physiological states are going to be next? That's MZ. And how do you predict any of these neural network weights are going to change? And everything, so what's inside Z is everything we can measure from an experiment. So we can't measure the neural network weights. There's some physiological states we can't measure. But everything we can measure, we collected Z, and we compare it to incoming data. And now we have an error signal, because what our filter is saying we expect is different, maybe, from the data coming in from the experiment. And we use that training signal to adjust the states a little bit, and importantly, to adjust the neural network weights. And if we run this for long enough, eventually, we hope, the neural network weights settle into approximations that make good prediction of the incoming experiment. And by the end, we'll have, we hope, a trained hybrid neural network traditional differential equation model. And so you can take a look, like stylized, this is what's going on, right? We've got our hybrid model here. We run it forward to get our simulations. We use the filter to compare to data. So moving forward, the first step is to see if this works in a simulated environment. So we've got collaborators who are really good at mathematical modeling at University of Maine, and they made this kind of simplified urinary tract. So it's missing some really important things like the brain and the urethra. So it's missing a lot of stuff, right? But it's simple enough that we can get started, and it produces the classic lower urinary tract behavior of a filling phase, and then bladder pressure is rising here, and at some point your bladder squeezes to evacuate the urine, and then the volume drops, pressure drops, and then the cycles continue. So it simulates this classic low pressure filling phase and high pressure voiding phase that we see in the urinary tract. So now we can run this, and what's going on here is just a traditional model, right? So these are all known equations, and we're just integrating this. But what this lets us do is pretend that we don't know one of these states or equations and see if we can recover it with our method. And in this case, we'll know whether or not we're right because we have the ground truth for everything. We know what it should be. So there's no actual data involved here. It's all simulated data. So let's pretend that we don't know the equation for the mass balance of urine in the bladder. Let's pretend we've now learned that. So now what we're doing is, instead of an experiment, this data is all coming from the simulated model, right? And we run this hybrid model, we put our filter in here, and we see if we can recover the simulated data. And the answer is yes, we can do it. So right now the AI is replacing that urine volume puzzle piece. And so here, we add noise to the model for measurement, that's in black. And in the gray is our hybrid model estimate of those states. So it's perfectly aligned on top. That's not so impressive because we know those equations and we're measuring the output, so that should be correct. But the cool thing is that in this pinkish trace, this is what the missing puzzle piece says that the mass balance, the urine in the bladder should be. And here is the actual ground truth in the dashed line. And so without knowing the equation for the mass balance, and without having a measurement of what's in the bladder, this hybrid model has inferred that it must look something like this. Right? So this is really encouraging. I mean, maybe there's a little time lag, and you tweak parameters and try new ideas for training, but this is like, this is really exciting that you can do this kind of thing. So now you take it a step further, and you do it with the experiment. So now, we actually do not have an equation, in point of fact, for the bladder afferents, the sensory neurons coming off the bladder. We don't know how they work, right? I did one for the urethra, no one's done one for the bladder, they're really hard to measure, so we don't have it. So let's get data that we measure from the rat, but we don't measure this. We don't measure the output of the sensory neurons in the bladder because that's very hard data to get for complicated reasons. So now let's measure all the other stuff though. Let's measure pressure in the bladder, let's measure the volume in the bladder, all that. And we've got our hybrid model now. So these are the equations we know. We know the mass balance, we know the pressure, the equations for pressure in the bladder, but we don't know this. So now I'm not going to be able to show you the ground truth, right? I can show you the model predictions, but I can't show you ground truth because we don't know what it is. That's what we're trying to estimate. How do we do? Well, maybe it's a little more complicated to explain here, but for the black, again, the bladder pressure measurement, our hybrid model estimate in gray tracks exactly. That's like a prerequisite, right? We want to make sure that a model is predicting the actual measurements that we get. The same for the bladder volume, perfect match. And now for the bladder afferents. What I'm showing you here is the model learning in real time. So I'm showing, we start from total naivete, and the data starts coming in, and now this missing puzzle piece starts getting trained on. So at first, you see this smooth increasing curve. There's a huge contraction of the bladder, but the model predicts nothing from the sensory neurons of the bladder. That's got to be a mistake. Right? But by the second voiding event, already the model is starting to predict an activation of those sensory neurons responding to this, except this is happening much later than the actual contraction. Well, that's got to be a mistake, right? Because the neurons are going to be sensing the contraction as it's happening. But then already, just by the third event, the model already figures out that in order to capture the appropriate behavior, it's got to be reacting at the moment that this bladder contraction is happening. So this was so encouraging for us to see because it's a very plausible result that this hybrid model was able to learn without any information about the afferents at all. We didn't measure it, we didn't tell anything about the structure of the equation. The only thing we did was say, these are the physiological states that we know influence it, right? So it is still a circumscribed puzzle piece. We say, we know that these states are going to be going in influencing what you're sensing, and this is what you're going to give us out. We're going to force you to give us the sensory activity of these neurons. You're able to do it. And now, in my opinion, the most exciting piece. It's one thing to always have the model in conversation with incoming data from the experiment during training. It's another to ask, is what your model learned an accurate representation of the missing physiology? the only way to test that is to pull it away from the experiment and see if it works on its own. So now we've removed the data, we've removed the Kalman filters that make the small updates and train the model, and now we're integrating this hybrid model as though it were a traditional set of ordinary differential equations and asking whether or not it produces reasonable results. And if it does, we would feel comfortable doing things like running computational experiments. We'll say, if this represents the actual physiology, we can do things like, in the computer, test, well, what happens if we zap this nerve or that nerve? Do we get a relaxed bladder or a contracting bladder? Do we improve reflexes or does it make it worse? And then we can run 10,000 digital experiments rather than 10 experiments in these painstaking electrophysiology setups. So that would be huge. Okay, so what do we find? So these blue traces, this is for bladder pressure, and this is for the volume in the bladder. And these are coming from the equations that we stipulate that we know. Right? So these are the equations we've written down. And we see this low pressure filling and these high pressure voiding events. You can tell that the bladder is voiding because it's lined up here with a drop in the volume that's inside the bladder. And this is what the missing puzzle piece predicts for the bladder sensory neurons. And it looks so plausible, right, in integration. And so here you see, as the peak of bladder pressure comes, we have a corresponding peak in those afferent signals, the sensory signals. And you can even see they start ramping up as the pressure here starts ramping up even before, right? So this is fantastic. So it turns out that I'm showing you the best result that I have. There's a lot of difficulties, right? There are some models that we know this doesn't work for. There's technical observability issues. As the model grows in size, you have to deal with more and more complicated things, like if you're missing two separate components that are talking to each other, that creates another set of problems, right? But what we have shown here is that there are definitely cases, and important cases, where we can learn the underlying physics that look a lot like the actual physiology we see. And this is just in a simple model. Like, we're working on more complicated, realistic models of the lower urinary tract, for which we're going to try to learn these missing pieces in the future. So already, this is really great results, and we've shown for tons of other simulated systems that this works. So we know the types of systems that this will work for and where we have trouble. So, in conclusion, I think that if we are willing to be a little bit more creative about the models we use and combine the best aspects of each, we can create hybrid models that have an advantage over the existing things that we have. And I think that focusing on these two relatively different scientific fields, I mean, they're both nervous system control of the body kind of fields, right? But they're very different regions of that space. And they both led me to the conclusion that it's okay to kind of mix and match these things. You can think a little bit more creative about it, and it gives you a lot of power that you didn't have with each individual piece alone. So when you're thinking about, in your research projects, wow, I really want to test this, but I don't know. I don't have the math to do it, or the experiment rig we've got just doesn't take those kind of measurements. And maybe it's time for a different kind of model, something else to explore. Thanks.
Questions?
What's a neural network weight?
Did you ask what is a neural network?
Neural network weight.
Weight. What is a neural network weight? Yes, good question. So, an artificial neural, so a traditional equation, think of, I'm going to get kicked out of here if I write on this. Okay.
You already picked up.
Yeah. A traditional equation, the weights of that equation are its parameters. So if you think of a line, y equals mx plus b, the parameters or weights of that equation are the m, that's your slope parameter, and your b is your offset parameter. Neural networks are equations of that kind, except instead of having two parameters, which we understand what they represent in the equation, there's like 1,000 of them, and we have no idea what they mean.
Yeah.
But nevertheless, they're all coefficients on simple functions of that kind. So when I say weights of a neural network, I literally mean the values of those coefficients in front of the terms in the mathematical model. So,
Oh, go ahead.
You have mentioned you have developed text signals, which then you translate into neural signals. What specific signals do you retrieve from the graph that you transfer?
yeah, great. So the question was, what exactly are we recording from this virtual reality glove that we then use to simulate neural signals? Imagine a kind of a spandex glove, and you stretch it over your hand so it fits very snugly. And across all of the joints in your hand are stitched something called piezo-resistive sensors. Basically means as you stretch them, they emit different amounts of current flowing through the circuitry. So what we literally measure is how much those sensors are stretching over each joint, which is a proxy for what are the shape of your finger joint angles. So we pull about 20 dimensions worth of data off of the hand. So from the joint angles of the participant's hand, that is what feeds the small artificial neural network that then generates the simulated neural data. And that's usually an expansion. So normally we'll get 20 signals from somebody's hand, and from those we'll simulate something like 100 to 200 artificial neurons.
Maybe a question from both sides. So for your decoder, and this is going to simplify the situation that you have now taken away the ability to move in any direction. Would you expect ever, if you could train for an infinite amount of time, that the more degrees of freedom would ever perform better, perhaps faster, if someone could ever truly understand how to navigate that space? That's for that side. For the second part of the talk.
Well, I'm going to make you remember your own
Okay.
question.
Yeah.
Yeah.
But the second part of the talk, is it possible to go from these artificial neural networks where you have more the black box part of the hybrid model to more traditional physiology and some kind of deterministic differential equation that you could eventually learn how the physiology works based upon what you're doing, if that makes sense?
Okay. So first, never miss an opportunity to insult me by calling my situation simple. So if we let somebody practice indefinitely with the more maneuverable decoder, translator, wouldn't that ultimately just be better than kind of locking people into this sort of fixed direction decoder? I think that's just an empirical question. Like, we'll see. What we have seen is that we have records now of people using these brain-computer interface systems, the implanted systems, to doing maneuverable cursor control for over 1,000 days. And they improve, but there's a plateau. Right? They don't improve indefinitely. And we have seen the same thing on shorter time scales in our model. Now the thing to keep in mind about these systems is it sounds like, I was trying to be careful not to say this, right? It sounds like in brain-computer interfaces, what the technology is doing is mind reading. But that's not what's happening. Right? We don't get intentions from the brain. What we get are totally abstract and indecipherable squiggles on a computer monitor. And we've got to make sense of what those mean in the context of what somebody might want to do. So really what's going on is we set up the system, and people have to learn like a new skill, like they're learning a new video game or an instrument or something, how to interact with these systems. That's really difficult. It's not effortless. And so we think that constraining people to these different directions are really helpful for that. And there's always the possibility that your intuition is right, and what we might end up doing is relaxing those constraints over time. And we've been looking into like automatic ways to do that kind of thing too. Okay, so your second question was about what are the limits of what we can tell about the physiology.
Can you teach us something about physiology based upon what you're doing, other than just knowing how these afferent signals may look?
Right, right. So, one of the things that makes the approach we're working on powerful could be seen as a liability also, which is we need to define that puzzle before we start. So every one of those small neural network models gets put into one of those missing puzzle pieces. But we have to say what that puzzle is. So if we know nothing about the system, then we can't use this approach, and we won't be able to invent any new knowledge about what's going on. But if we know enough about the system already that we can make that puzzle piece map, then 100% yes, right? If we know that there's something right there that connects these two pieces, but we don't know what it is, we can learn it. And then once we have learned it, we can start probing it. We can do these computational experiments, we can see its dynamics. One of the things I didn't show, I wonder if it's worth it to too much. One thing that we can show is we can discover an ion channel in a neuron. So we use this very famous 1950s Nobel Prize winning model, computational model of a neuron, which has these pores in it that lets in and out the chemicals that help generate electricity. And we said, what if we know that there's one of these pores there, but we don't know what it is or how it works? Can we discover it? And the answer is yes, right? We can discover the dynamics for the potassium activation in that ion channel. So if you can build the puzzle piece map, I can give you new knowledge, but if you're just so dumb that you don't know what it is, right, then you're back in the world of regular art.
Well, you tell it, hey, I think potassium activation channel, then tell me, oh yeah, it is. Or
You don't have to name it. Right? So all you have to do is say, there is an equation or a set of dynamics that connects these two pieces, or three pieces, or whatever, and then we can discover the approximation of it.
There's a student in the back there that has a question.
Oh, yes. You, the excited one in the back.
How nonlinear your observation equation, where in that space model and the second is, after you feed that model to the real data, how close to white noise was your innovation ever?
Okay. I don't know how to bring the rest of the audience along with for those questions. How nonlinear? So we try very hard to keep the measurement model linear. So we will rewrite our differential equations so that the left-hand side is expressed in something that's almost exactly what we measure to get rid of those nonlinearities. So how to explain that? We want to make sure that the measurements we get from the experiment, we can fit directly into the model for training data. That's the idea. So we don't have to then do a bunch of math on the things we measure to get it to fit in the model. We try very hard to make sure we don't have to do that. The second one is about the common filter innovation. If you remember back to your statistics class, when you fit a line or a model to your data, what you're hoping for is that the mistakes you make look like a bell curve. And that says that you can't do any better or worse, all that's left over is noise. If you fit your data and the errors that you make have all this structure in it, well, that's a sign that you could do better with your model, you could fit that structure. So the excited student in the back, their question was about, well, what do your errors look like? It has to do with the innovation in the Kalman filter. So for there, most of the states, most of the time, look white. They look like you unbiased. You can't do better, or at least we don't see any structure in the residuals. Now, the caveat to that is there are regions of the state space where that doesn't quite hold. So the idea behind the common filter predicting like where your state is next is that you take a couple of guesses, kind of, right? So you get a measurement that you're right here, and the common filter says, well, that's where the measurement said, so you could be anywhere here. Like mostly we're gonna guess you're around here, but yeah, you could be out here, you could be out here. Now that works fine when you're driving in your car and GPS is running, because if you're over here, you're just on that street. If you're over here, you're on that street. If you think about some of the equations I talked to you about here, suppose you're working with the mass balance of the volume in the bladder. If you sample a point over here, and that says, well, let's see let's consider the case where the bladder has -2 milliliters in it. That will destroy everything because the differential equations are not made to handle negative numbers. You get everything runs away. So there are regions in state space where you have to put guardrails up, and then the errors that you get are not totally white, and that's a huge problem. It's one of the technical things we gotta solve. Yeah.
All right, with that, let's thank Dr. Danziger again.